All right, it's 2:03. I think we can get started. So hello, everyone. Welcome to ASIC Seminar Series. This is John, and I will be the moderator with our communication specialist, Cassie Medley. And I would like to thank you for coming. This is our first seminar in spring 2024. And this semester, we have a list of fabulous speakers, as you can find in our previous email announcement. We have Inês Azevedo, the speaker today from Stanford University, and we have other distinguished speakers such as Dania Kirchbaum, the director of the Earth Science Division of NASA Space Flight Center, and Professor Neil Donahue, director of Carnegie Mellon's Sternberger Institute, and we have Tracy Holloway, a professor from UW Medicine and a member of the National Academy of Medicine. And so you can go to our seminar calendars to take a look on our seminar schedules. And just so you know that this one is being recorded, and we will publish the recordings on our YouTube channel. And right after the presentation, we have the Q&A session. So please feel free to bring up any questions. We suggest you unmute yourself and ask a verbal question, or you can chat us your questions, and we will read it out. Today we have our distinguished speaker from Stanford University, and before she gets started, I will have Cassie to introduce the speaker's background. Cassie, please proceed.
Thanks, John, and thanks everybody for being here. I'm just going to talk about our speaker for a minute. Inês Azevedo is Associate Professor in the Department of Energy Science and Engineering at Stanford University. She also serves as faculty in the Global Environmental Policy Social Science Division and is Associate Professor by courtesy in the Department of Civil and Environmental Engineering at Stanford. She serves as Senior Fellow for the Woods Institute for the Environment at Stanford University and Fellow for the Precourt Institute for Energy at Stanford University. She is the co-director of the Bits and Watts Initiative from PIE at Stanford. She is also invited professor with the Nova Business School in Portugal. Professor Azevedo's research interests focus on how to transition to a sustainable, low-carbon, affordable, and equitable energy system. She is interested in sustainability and energy issues where a systems approach is needed by combining engineering and technology analysis with economic and decision science approaches. Her current interest is to address energy issues with a particular focus on distributional effects and equity. So with that, I'm just going to go ahead and hand it over to our speaker to give her talk.
Thank you so much, Casey and John, for the wonderful introduction. So today we'll be talking about strategies to reduce climate impacts and their pollution consequences when thinking about electricity and transportation changes in the US sector. Part of this would be with an emphasis on distributional effects and environmental justice. Before I do so, and in terms of a broader introduction, I'm really happy to share that here at Stanford University, we recently created a new school of sustainability. The school is just 1 year old. That includes all sorts of new departments and groups, as well as cross-cutting institutes. The school is rapidly growing, and there is also the opportunity for graduate studies that are emerging. And so I just want to put that out there, as this is a wonderful opportunity to engage in new interdisciplinary research focused on a world transition to sustainability and a more sustainable future. With that, I would also like to share this slide. It seems like a busy slide, but those are the graduate students that I had the privilege to work with in the past and mentor. And so the work that you'll see today has emerged mostly from their effort and creativity and research. And from those, there is the subset of students highlighted that are current students and close to wrapping up and hitting the job market. And so I would love to put you in touch with several of these students if there is interest in the subset of work that I'll be presenting today. So to this audience, the sorts of trends would likely be familiar. Climate change, which was, upon growing up, something that was perceived as being impacting the far future, is indeed, for many of us now here and now, and with some of the significant changes already materializing, though there is still some uncertainty to the magnitude of such. In this figure that was produced by Antti Lipoten from NASA, using data from NASA, we're looking at the temperature anomalies by country from the 1880s and up until 2017 for different countries. And the base period considered in this particular animation is 1951 to 1980. And what we can observe is that as the time lapsed in this animation, a lot of these countries and regions have seen an increase in the trend of their temperatures towards what appears in the animation as orange-red. So the anomaly is starting to be more significant. Now, in addition to that, the window of opportunity to achieve the 1.5 degrees C in increase on global average temperature is kind of rapidly closing. In this plot, I'm showing the global warming, again, relative to 1850, between 1850 and the 900 period. And the various types of scenarios brought up by the IPCC. And one of the key things is that though these are not projections and are different types of scenarios run by the IPCC, we see that for along the range, the wide range of scenarios observed here, a commitment of at least 1 degree C increase, and most likely, if we can remain on the continued trajectory that we observe today, quite higher than that, is becoming apparent. Now, at the same time, we remain in having the need for energy to grow our economies and to provide the services that are needed across the world economies. One of the things that is helpful, though, is to have a sense of how are renewables and low carbon energy sources growing versus other sources of energy. In this plot, we're just looking back in terms of the historical context from 1965 until recent years. And the key point that I want to stress here is that despite the growth and prevalence in green technologies, which is wonderful to see, sort of 84% of our primary use globally still relies on fossil fuels. And so there will be a long-term need for a change, but also being cognizant realistically that the fossil fuel sources still power the backbone of many of the economies throughout the world. In some of the position points that I've shared in the past, one of the key ones was a guest essay for the New York Times with several colleagues, and just stressing that despite the fact that we don't know exactly how this transition towards low carbon economies will occur, we are kind of wasting time thinking about exactly what will be the composition of net zero energy systems as we think along. Some of the next steps are clear. We need to increase the amount of renewables. We need to increase the amount of storage supporting those variable renewables. And some of the renewables are becoming cost competitive in some locations. So in terms of what we need to do in the electricity sector throughout, there are several pathways that can achieve there. And the critical thing may be to not necessarily focus on having a perfect portfolio of energy sources and technologies, but making progress along and getting that transition to new energy sources with a low carbon footprint advancing rapidly. At the same time, and more recently in the Scientific American, I discussed the fact that indeed in some locations, not everywhere, options such as solar PV and wind are achieving cost parity or being even cheaper than some of the conventional electricity generation technologies. But with that said, they also come with some challenges given the variability of those renewable energy sources. So this hopefully sets the stage for some of the research that I will show. With one more dimension, which is when we think about the literature focusing on decarbonization of energy sector, often that focus on how to transition away from the fossil fuel energy base that powers these economies, and focusing on greenhouse gases such as CO2 and methane. And this, as you well know, will have a global dispersion. It will stay for a long time in the atmosphere, and we'll see consequences that will be overall global in nature, though differentiated in terms of those impacts. What is often separated and in a different body of research is the fact that that same fossil fuel energy also has emissions of health damaging air pollutants such as SO2, NOx, and primary emissions of PM 2.5. And those are very different altogether because though they can have somehow a large dispersion, the consequences will be much more localized than in the context of greenhouse gases. The health damages from those air pollutants will depend on where they are emitted, how they disperse, where the concentration is increasing for PM 2.5, and how many people are exposed to that increase in pollution. Also, they have different characteristics where if we turn off the knob on the emissions of these sorts of criteria pollutions, they have a very short lifetime in the atmosphere, and we can see the concentration going down very rapidly. So due to very different types of air pollutants, when we think about criteria pollutants that have damaging health consequences through PM 2.5 formation and the greenhouse gases characteristics. What my group has been doing is emphasizing the need to design policies and take into consideration both the greenhouse gas implications or benefits associated of reducing the emissions of greenhouse gases and the air pollutant consequences from pollutants that have health damages associated with that. Why do we care about PM 2.5? Well, turns out that PM 2.5 is the largest environmental health risk across the globe. It is responsible for about 5 million deaths annually. It is associated with increased mortality rates from cardiovascular disease, chronic obstructive pulmonary disease, and lung cancer. And the fuel combustion of both gasoline, diesel, and coal, to less extent in terms of pollutants coming from natural gas, will result in emissions of both primary PM 2.5 as well as SO2, NOx, which will react with ammonia in the atmosphere, forming secondary PM 2.5. Here to the right, you just have an illustration from our rolling data on the number of deaths by risk factor across the world in 2017. And the contribution of air pollution, I believe, is decreasing slightly from year to year, but still being one of the most important contributors. And so, as I was mentioning previously, climate change and air pollution consequences and the associated policies to tackle these two externalities have been assessed mostly in isolation, but there is a very strong case to start thinking about them in conjunction and understanding what types of strategies may provide a win-win strategy from both the perspective of climate change and air pollution reduction. So my group has developed a series of tools and open source decision tools to try to understand how decisions for decarbonization in the electricity sector and in transportation could reduce the emissions of CO2 and their consequences, could reduce the health damages from air pollutants, and how much would this cost? Here's an example where we developed for every single grid across the United States, open source models that show both the generation emissions and costs of generation of every single power plant across these regions. Here in the top, you see 4 different regions. So the Western region, Texas, and RFC, the generation costs associated with producing electricity. We list those by plant type. And then in the plot below, you see matching it, the CO2 emissions per megawatt hour associated with each of those respective plants shown in the top. And this is important because as we pursue strategies such as adopting electric vehicles, and those are charged at different types of the day, we can now have a better grasp of the emissions that are induced or avoided through electric vehicle charging in each of those specific regions. Similarly, if we think about energy efficiency or demand-side management strategies, we can now track the emissions closer to what is observed in reality, rather than assuming regional average emissions factors. As I mentioned previously, though, while we care about the emissions of CO2 and air pollutants, in the case of the conventional criteria pollutants, where they are emitted, where they increase the concentration and the amount of people that are exposed to such pollution levels will also matter. So another open source tool that we created and that's welcome any modeler to start using it is a repository of electricity sector impact factors estimates. So this tool enables you to select whether you want to look at emissions and damages from CO2 and from air pollution on the basis of generation or consumption. It allows you to select whether you're interested in average emission factors in a specific time horizon or marginal emissions factors, meaning trying to identify the last plant that is needed to serve a certain amount of load at a certain point in time. Whether you're interested in downloading emissions factors that are really centered on emissions, or use other metrics like damages per megawatt hour of electricity generated in a location, can then download the data using either NERC regions, states, or balancing area regions. And you can look at data all the way from 2010 to 2018. We need to update that now with more recent years worth of data on the tool itself, though we are able to support you with those data if you email us and are interested in using those directly. So by mapping this out, we now have metrics of damages in terms of premature mortality or dollar values associated with premature mortality per kilowatt hour of electricity generated in different locations across the United States, providing a powerful tool for policy guidance. My colleagues at Stanford, Jacques Chalandar and Sally Benson, took this effort one step further on the greenhouse gas emissions front. They tracked consumption-based emissions for every single balancing area across the United States. If you're interested in seeing just on an hourly basis how those have evolved, they have that available at energy.stanford.edu/grid emissions. And so what they're using over here is just publicly available data, including SEMS and average emissions factors when no further information is available, but taking into account imports and exports across regions and really taking into account these power flows across regions so that you can have information on the CO2 emissions associated with, again, either charging your vehicle, promoting energy efficiency strategies, on a consumption level based on the electricity that you're using from the grid rather than the electricity that is generated within a geographical area. Now, the strategy to do this accounting of consumption-based emissions that Jack and Sally developed was actually incorporated by the US Energy Information Administration. So they are now following also their method in terms of assessing those emissions. And finally, we want to bring this to the lenses of distributional effects as one of the subset of issues of concern when thinking about environmental justice. As I mentioned previously, globally, air pollution is one of the largest environmental health risks. It is also one of the major health risks in the United States. In the United States alone, it is responsible for more than 100,000 fatalities. And though electricity generation has become cleaner over time in terms of its contribution to air pollution as we moved away from coal, the contribution from electricity is still quite significant and will be the focus of some of the work that I'll share in the next few slides. The electricity generation and decrease in coal has been owed mostly to two facets. The first one being the adoption of air pollution control technologies in the stack of coal power plants, owing to environmental regulations like the Clean Air Act, as well as a recent transition from coal to natural gas that was driven originally by low natural gas prices. Now, we were not the first ones thinking about quantifying the damages from electricity generation associated with PM 2.5. There were several existing estimates that range from 10,000 to 52,000 premature deaths per year associated with electricity generation. And the wide range of estimates that you observe is dependent on several different things. One is that things are changing from year to year. And so those studies range from being produced in 2009 all the way to quite recently. Some of those results have been published in the last couple of years. In addition to dependency on what model was used and the degree of complexity and detail in those different models. In any case, we do see that electricity, even in the lower bound estimates, is still associated with about 10,000 premature deaths per year. And while that part of the puzzle had been addressed, the demographic distribution associated to the exposure from air pollution from electricity generation was largely unknown. And thus, we contributed to that gap in the literature by estimating the exposures to and health impacts of PM 2.5 from electricity generation. And we did so at different regional boundaries, namely doing it for the 7 regional transmission organizations or RTOs. We did so too for and from pollution from different states. And so we'll look at transfers in air pollution across states in a little bit, as well as by income and by race. So this resulted in this piece in environmental science and technology, where we really focused on the distributional effects from air pollution associated with electricity. And this was thanks to a wonderful collaboration with Manny Tint, Chris Tessam, and Julian Marshall. How do we compute the damages from air pollution. We rely on models, and in this particular instances, we used reduced complexity models called integrated assessment models for air pollution. And what these models do is we start with a detailed inventory of all emission sources for PM 2.5, SO2, and NOx. And then we quantify what is the concentration in using a spatial grid of resulting PM 2.5 associated with those emissions. And then we assess what are the premature deaths associated with that baseline level of concentration using those response functions and information about the population exposed to PM 2.5. We then, after that baseline run, rerun the model, but now with the perturbation on the emissions for every single source one at a time. So we take the emissions of power plant A, add them, and understand how the emissions of that power plant A would increase or change the concentration of PM 2.5 in the spatial grid. And we do that for every single source of emissions, both for point sources for power plants, as well as when focusing on transportation, we look at changes in emissions in the form of ground level area source emissions. And by doing this procedure of incrementally changing one at a time the emissions from those sources, we're then able to attribute the premature mortality associated with those sources to the emissions observed in our data set. In order to assess the premature mortality, we need to have information on how people respond to different levels of PM 2.5 concentration. We rely on studies that have previously been done following cohorts of populations in different locations and taking into account their exposure levels. And namely, we use the American Cancer Society dose response function for this particular study. Now, as we go through these steps, and we used INMAP, which is a reduced form air quality model that was developed by Julian Marshall, Chris Tessam, and others. And we that leads us to the results that I'll walk through now in the next few slides. So first, in terms of the national picture, we find that more than 16,000 premature deaths are attributable to electricity generation in the United States. This amounts to about 4 premature deaths per terawatt hour of electricity service provided to the nation. Most of these premature deaths, 85%, occur within the scope of an RTO, and I'll show the map in just a few seconds. So to power plants that are located in those regions. And we find that 90% of the premature deaths from electricity generation nationwide are associated with coal electricity generating units. Okay, here on the map on the right, I'm showing the different RTO regions, and the colors of the map represent the share of coal to the total electricity generation in a year across these different RTOs. Table 1 shows the estimated deaths per unit of electricity generation for each of these different RTOs. And I would just highlight that the largest total premature deaths occur in PJM, which is here shown in navy blue, and in the MISO region, which is in a dark blue color, 2 regions that have a large portion of their electricity generation from coal. You'll notice also that we have SPP as a region that had a large share of coal in the electricity generation. We observe a slightly smaller total premature deaths, but a large number for deaths per terawatt hour. And this just ties to the population density on these states being lower than some of what is observed in MISO and in PJM. We then looked at premature mortality by different demographic indicators. And so here on the vertical axis, we are showing premature deaths per 100,000 people from electricity generating units and associated with the resulting PM2.5 NOx and SO2 emissions and resulting change in concentration. So here, though we list PM2.5 related emissions, we are indeed taking into account also the emissions of SO2 and NOx and their formation of secondary PM2.5. In the horizontal axis, we have some of the race and the ethnicities found across the United States. And so if we think about the average premature mortality across the nation, we find that premature mortality associated with electricity generation across the United States amounts to a little bit over 5 premature deaths per 100,000 people. But when we start looking into the differences by race and ethnicity, we do observe that Black African American have a higher level of exposure and higher premature deaths, followed by white non-Latino. We may wonder how this relates to also the level of income. Here we see the same vertical axis in terms of premature deaths per 100,000 people. Again, just in terms of premature mortality from the electricity generating units. The horizontal axis is displaying household income groups in $1,000. And the size of these circles is representing the population within that income bracket. And so we observe that for the US population-wide average, as the level of income increases, there's a slight decrease in premature mortality. We also observe that across all income levels and brackets, Black African American are always having the highest level of exposure, and there is some attenuation for the higher brackets, but still fairly higher than for any other of the groups, followed by the white non-Latino, which generally also have an exposure higher than the average for many of the income brackets. Now, that's one level of distributional effects of interest. We also wanted to look at consequences for different states. And so in this set of maps, we're looking at both total self-important and exported damages associated with air pollution from generating electricity across those states. So let's walk through this panel step by step. In panel A, we are displaying the premature mortality in each of these states associated from emissions of PM2.5 and their precursors, regardless of where the emissions occur. So some of the effects that we'll see here in Pennsylvania may be tied to emissions out of a stack of a power plant that is located in Ohio and vice versa. We observe and conclude from this panel A that there is a wide disparity in premature mortality between each state's boundaries, with some of the states such as Ohio, Pennsylvania, and Texas having really quite high numbers in terms of observed premature mortality. Then in panel B, we're looking at a different indicator, which is what is the portion of premature mortality between the state boundary that is due to emissions of air pollutants also within that state boundary. And now we see that the numbers, for example, for Ohio decrease by quite a bit, Same thing for Pennsylvania, taking those as an illustration. This means that the premature mortality that is observed between the state boundaries is due to pollution that is coming from elsewhere, not necessarily a lot of it from the states itself. Panel C is showing us the damages from air pollution that are induced to others. So this represents the premature mortality that occurs in one state due to emissions that originated in some other state. And so here we see that a large part of the damages, again, selecting Ohio and Pennsylvania, that are imposed on others are quite large. And finally, in the last panel, we're computing the difference between B plus C minus what we observed in A, representing the net health damages that are observed between a state. So this will be the total health damages inside the state from emissions in the state, plus the emissions damages to others and minus the damages between the states. And the large negative number for New York is interpreted as a burden of air pollution damages that are faced between the state of New York due to emissions from elsewhere and not really in New York. Now, all of these results were focusing just on the air pollution portion, and I didn't highlight the connection with climate change and the emissions. So in a follow-up work with my former PhD student, Brian Sergey, who is now at NREL, we looked at how could we optimize the emissions reductions from US power sector when thinking just about the climate benefits associated with reducing greenhouse gases and the health benefits associated with reducing the emissions of SO2, NOx, and PM 2.5. A little bit more on the broad context. As I promised, we wanted to take into account both the climate and air pollution benefits. And in particularly, what we've seen at the federal level and state level policies is that often one would consider the potential climate policies and treat air quality and health as co-benefits from the climate policy. But as I'll show in the next few slides, the solutions that are to be pursued when you co-optimize together for air pollution and climate may be quite different under specific CO2 emissions reduction goals. And so we did that exercise to see what sort of strategies would be worthwhile. Though there was some previous work previously on both the air pollution and the climate change side, we were the first ones to bringing up the links between those two by producing a co-optimization of damages reductions for both climate and health, as well as taking into consideration the costs of transitioning from the current electricity generating infrastructure to a new infrastructure that would have less emissions and less consequences. So how do we do that? Well, we developed a linear optimization model that minimizes the total costs subject to a constraint in achieving a certain level of national CO2 emissions reductions. We tested this with 30% emissions reductions for CO2 from a baseline year. And so when we think about the total costs, this means really minimizing the cost of building new infrastructure and not using the existing infrastructure. The costs associated with CO2 emissions times the social cost of carbon, here labeled as SCC, for every single power plant J, and the marginal damages from air pollution for a certain power plant J and for pollutant P times the emissions associated with power plant J and for pollutant P. This W portion over here indicates whether we want to consider also explicitly the benefits from reduced air pollution, or ignore them in the optimization function and just track the consequences as co-benefits from a climate policy. And so we built this model with different types of alternatives of new generation technologies, including wind and solar. Wind and solar, we assumed, were always paired with storage as a way to provide firm power, or natural gas, new natural gas combined cycle power plants as an alternative. And so what did we find? Here in the vertical axis, we have the annual damages in $1 billion. The horizontal axis shows us the baseline emissions. So this represents the electricity sector as we have it today. The second set of results and markers correspond to the annual damages when we are optimizing our system to achieve a 30% CO2 emission reduction, and having in the objective function just costs plus the benefits of reducing CO2 emissions. And finally, in the health plus climate damages, we are explicitly accounting for health damages in the objective function itself. We've run these simulations across using 3 different air quality models, AP3, INMAP, and EASIER. And we also consider different concentration response functions. The American Cancer Society one, which was the same one that we used in the previous study, and the Harvard 6CT study, which is an older study than the ACS. The reason for running these different sensitivities is that there is underlying uncertainty on both the concentration response function, as well as regarding the structure of different air quality models. And so we wanted to have a broad understanding also of what will be the uncertainty and variability in the results. So if we look first at the baseline, we observe that under the current conditions, the emissions of CO2 from the grid, if valid at the social cost of carbon of $40 per ton of CO2, are inducing close to $70 billion in damages per year. In addition to that, the electricity grid as we have it has also air pollution consequences. And so we see the wide range of values. I'll refer to the ACS for the rest of the talk. We see damages between 30 and a little bit under $60 billion per year from air pollution damages. Now, if we impose the 30% emissions reductions across the electricity generating fleet of the United States, we see that, unsurprisingly, the emissions and damages from climate change decrease by 30%. And we indeed have a co-benefit in terms of the air pollution related damages that also decreases substantially. So an important co-benefit. But if we explicitly co-optimize our decisions for both costs, climate change, and air pollution damages, once again, we achieve the policy stringency of reducing emissions by 30%, revealing that this continues to be a binding constraint. But we achieve much larger damages reductions for the electricity sector. Now, economists that will be in the audience would ask me, how much does this cost, however, to implement? And so here we're looking at the same results as previously. So for the 3 air quality models, in this case, we're showing the results for the ACS dose response function. Vertical axis is once again annual benefits in $1 billion. And so we see for C, which is the climate only, including only climate as part of the objective function, whereas in the second set, H plus C, we include both health and climate in the objective function. So what we observe is that we have health benefits all across all models and scenarios, We have the climate benefit, once again, valued at $40 per ton of CO2 that remains unchanged across all scenarios. And here in the dark green bars, we're showing the costs of mitigation, meaning the costs of building and retiring infrastructure to achieve these goals. Overall, what we observe is that if we do the societal benefits minus the costs, we have net benefits throughout, which means that if the externalities associated with either just climate or climate and air pollution were considered, we would be doing this transition to new infrastructure. The choice of the infrastructure and its costs depends on our assumptions about future fuel costs. What you observed in our initial scenarios, which were done still under fairly lower natural gas prices than what we've been observing over the course of the last year, was that the choice was predominantly new efficient combined cycle natural gas power plants, whereas solar or wind coupled with storage would emerge under more higher natural gas price scenarios. This has tremendous implications across the states and the nations, depending on how we define these policies. Here, I highlight on the vertical axis on the left, the new capacity that would need to be installed to meet either the climate-only objective function in orange or the health plus climate in blue. The diamonds represent the share of the state capacity that would need to be replaced. So we see places like Texas where the share of capacity that needs to be replaced is actually in the range of 10, 12%, but still representing a large amount of capacity and with key differences when we start accounting for health damages explicitly being also reduced. Whereas other regions, let's take a look here at Ohio. If we're thinking just about the climate objectives, Ohio would need to replace a fairly small portion of its fleet. But if we take into consideration the health damages produced by Ohio electricity generating units, they would need to replace close to 30% of the existing electricity generating capacity. So I want to make sure we have times for questions. So I'll stop after introducing just the slide, which is that we then moved on to think about these issues in the context of also transportation. In order to do that, we started by understanding what are the health impacts from electricity imports across the United States. And this was done work led by PhD student and Nora Annecy, who is now a postdoc at ASU. And then we coupled this with information on truck flows and where trucks are commuting to think about the type of charging infrastructure that would be needed for long-haul trucks and the types of damages that could be associated with that. I'll jump to that just for reference, as this is interesting. So when we think about some of benefits from truck electrification, we can now identify that some of the current subsectors, even in the current grid, would make sense for electrification, given the amount of current health damages. And we can look at different types of benefits and strategies throughout. So with that, I'll stop here to give us at least 8 minutes for Q&A. There was more things to share, but I think I'll pause over here to make sure that we can address some questions and comments.
Thanks, Inês. Does anyone have any questions? You can raise your hand, you can unmute yourself, you can type it in the chat and I will read it out loud.
So I have a question where other people might be still thinking. So these conclusions are from based on the research in the United States. I wonder if the conclusions hold the same for other countries like European countries or some developing countries.
So I'm glad you asked that question, John. That's a really good one. So indeed, the conclusions and strategies are quite different depending on country and region and their fleet composition, as well as population density and so on. So we've been doing a lot of work regarding India. And in that context, we see that, for example, vehicle electrification in India would likely lead to an increase in emissions of CO2 and air polluting damages and premature mortality, at least for some vehicle categories. And that is mainly due to the existing coal power plants without air pollution control technologies. And since you asked, I'll also just highlight this part that I wasn't able to share. Hopefully you can see my screen again, which is we've built a database of all power plants throughout the globe and started devising mitigation abatement curves for every country. Here I'm showing the US, and so this is in the process of being published. We showed for the United States a US abatement curve, where the colors represent the type of technology that is being used, and the second word represents the type of technology that you're switching to. And we're showing the cost per in terms of dollars per ton of CO2 abated. We did this as an online tool that where you can run sensitivities, for example, to the discount rate. So here I'm just showing an animation on how the decision points would change based on the discount rate or based on your time horizon for the decision making, whether you are considering like just 20 years versus 100 years. And so happy to share more on that.
Very impressive. Thank you.
Yeah, Ross?
Really amazingly impressive and comprehensive talk. And I did have to step out just very briefly at the end of your talk because of a paper jam anyway. So I apologize if you addressed this, but you probably didn't. So I think that most people who study this would reach kind of the similar conclusion that you presented, although I don't think I've ever heard a more comprehensive and more in-depth analysis than your over the last hour. But, you know, we often struggle with how to pay for this, how to make it a reality. And, you know, because the health benefits or health detriments of fossil fuel are so dispersed. Okay, you know where I'm going with this. They're so dispersed, so widespread, and they're borne by others. And then, of course, there's these large upfront costs with renewable energy, which is also the bane of our existence. So, just do you care to comment on how to kind of take your great scholarly research into meaningful action, either in the U.S. or throughout the world, and how to get the message across and accelerate the change that's badly needed? Thank you.
Yeah, thank you, Ross, for this question. I would say that the easy answer is regulators need to regulate, right? In the sense that if the benefits are indeed there, what we've seen in the case of the United States was that a large part of these health benefits actually materialized thanks to the Clean Air Act, right? So if we do see that sort of implementation in other regions of the globe, that's certainly moves the needle for the air pollution consequences. In India, for example, one of the issues is that the installation of air pollution control technologies is actually sort of in the books, but it's not enforced. And so far, we don't see the same benefits in terms of a reduced air pollution, even if that's not a very costly strategy, all things considered. So I think the part on enforcement is going to be key. On the greenhouse gas emissions, as we all know, this is additional problems on responsibility across the nations and how to take that into account. I would say that I see the role of my group and the research team to be able to quantify these sorts of effects and present alternatives, being cognizant of the uncertainty and the fact that the optimal sort of decision paths are not what ultimately is going to be pursued, and making sure that we can provide this information in a way that is understandable to key decision makers, utilities, and regulators. Thank you, Ross.
Thank you. Sorry, I was trying to unmute. Thank you. Great answer. Thanks.
There's also a question in the chat from Russ I just want to read out loud. So Russ asks, when you calculate with cumulative impacts, how does uncertainty increase?
So in most, thank you, Russ, for the question. In most of the work I presented today, we're doing annual snapshots, right? So we are capturing uncertainty associated with both damages in the dose response function and emissions. So those are captured. The uncertainty across models is also displayed. We are not really using and capturing a crude uncertainty over a certain time horizon. So that's a good question, but we're not performing any sort of Monte Carlo analysis that would be able to capture, or Bayesian approaches to uncertainty that would be able to capture things over the course of a long time horizon. I'd love to do that. So thanks for the great idea for the next thing that we should be focusing on. That's so yeah, we'll consider that. Yeah.
Yeah, that's the cumulative impacts seem to play a pretty big role.
Mm-hmm.
They're complicated.
Yeah.
All right. Well, have fun. Nice study.
Yeah. Good point.
Any other questions before we wrap up today? It is 3 o'clock, so go ahead, Ross.
I always have questions, but you know, I try to just limit to one until I see other hands come up, but no one else. Have you had a chance to do a deep dive in this with the US EPA, and has it resonated with the US EPA? And preface this by saying sometimes the US EPA, hope I'm not going to offend anyone here, can be a little bit weird about outside studies coming in. So what's your experience you choose to share publicly with the EPA?
Okay, so the reduced complexity models for air pollution that we've been using have actually all been developed by colleagues in the air pollution space through funding from the EPA in something called the Cases Center. And they are the website for each of those models is publicly available. So, and it was in a call from the EPA for work on air pollution consequences and new modeling tools. So I believe they have been receptive to the results and be made aware through both the PIs and the entire research team, as well as annual meetings. I can't speak to what was done with that information, and I believe that those efforts are just now being wrapped up or coming to an end under that grant. Yeah.
Right. And I know the US EPA is presently reconsidering the ozone standard at some level. So hopefully work like this will help push it down. But of course, November 2024 is also looming. So
Yep.
Thanks.
Okay.
So unless we have one last minute question, we could probably wrap up. Just giving you a second just in case. Okay, well, thank you everybody for coming, and thank you, Inês, for giving us this great talk, for starting off our spring seminar series. I believe we do not have one next week. We have a bit of a like a break, but we'll see if some last minute ones are planned. Then we'll resume in a couple weeks. Thank you.
Thank you, everyone. Bye-bye.
Bye.